So today we're going to do something called solving linear trig equations. And we've done some of this in grade 11 in degrees, not in radians. So we're going to talk about how we do this in radians and what we kind of need to know when we're solving equations versus when we're proving identities is we need to know the difference between an identity and an equation. Okay, so in all of our previous lessons, we've been working with identities, left side, right side, that kind of thing. Now we're going to be working with equations. So the difference between an identity and an equation, I'll give you an example. Let's say equation versus identity. So a simple identity that we've been working with is that tan of x is equal to sine x over cos x. And this is called an identity because it's true for all values of x that we could sub in, as long as we sub in the same value of x for all the x's that are in here, for tan x, sine x, and cos x. So I can literally choose anything I want, and I will always get left side, right side, because this is an identity. Now, here's an equation. This is what we're going to be working with for the second half of this unit. For example, something like sine x equals a half. Now, this is not true for every value of x that I can sub in here. I won't always get left side equals right side if I sub in any value for x. This is only true for some values of x. And that's what we're going to be solving. For what values of x is this true? And this only happens at certain angles that I'll get a ratio equal to positive 1/2. So equations are only true for some values of x or for specific values of x. Whereas identities, where we have left side and right side, are true for all values of x. Or theta, or whatever it is that you're working with. We've done some identities with theta or whatever. Okay, so that's equation versus identity. So when we work with equations, we're going to be working to prove or solve, I should say, the values of x for which this equation is true. Okay, identities, we just prove that it is true for all values of x. Okay, so we've got a little decision-making process that we go through when we solve these types of things. And wherever possible, we're going to try to leave this in exact radian measure. So an answer like 5 pi over 6 radians versus the decimal answer of the 5 pi over 6. So in order to do this, we have a decision-making process, and it has 3 decisions that we have to make. The first decision is, can we use a graph to solve this? That's what we're going to ask ourselves. So graphs will only be useful for questions where you're working with sine x or cos x. Where the ratio that you're trying to solve the angle for is 0, 1, or -1. So questions with sine x or cos x equal to 0, -1, or 1. And the reason for this is that I have a graph of sine x that has key points at 0, 1, 0, -1, and 0. And then we have a graph for cos x that also has key points at those values as well. 1, 0, -1, 0, and 1. Okay, so when we can, so this is obviously 0, and then we had pi over 2. This one would be pi, 3 pi over 2, and this one happens at 2 pi. Okay, and then the same values for cosine 0. This one happens at pi over 2. This happens at pi, 3 pi over 2, and 2 pi. Okay, we'll zoom in here a little bit. So this won't make sense until we actually go and like actually do some questions. So for now, we're just kind of getting some of the groundwork laid out so that we have the decision process that we can look at as we're solving questions. So first thing is, I'm going to look at what ratio I'm solving for. If it's a sine or a cos, and I see that it's equal to 0, 1, or -1, then I will use the graphs to solve this. If that's a no, then I go to the second decision, which is, can I get my ratio from a special triangle? So you're going to ask yourself, is or could I get my ratio from a special triangle? For instance, if I had cosine of x equals √3/2, √3/2 we know comes from a special triangle. So I would use the special triangle to get my reference angle, and I'll use the cast rule. Okay, so √3/2, that would come from the pi/6, pi/3 triangle. Okay, other things that you might look for would be like if I get a tan or a cotangent that's equal to 1 or -1, if I get like something like 1/2 or 2 or √3/1, 1/√3, all of those kinds of things, those we can get from the sides of a special triangle. Okay, so first decision, graphs. Second decision, can it come from a special triangle? Third decision, if I've exhausted all those options above, then we go to calculator. Okay, this is always the last option because if I can leave things in exact values, then steps 1 and 2 are going to help me do that. If not, I use my calculator. We ensure that we are in radian mode. And we will use the inverse functions to isolate for our variable. Okay, so these guys on our calculator, usually we have to press like shift or second to get to these on our calculator, and they allow us to isolate for an angle when we're trying to solve questions like this. So everyone will need their calculator on hand for this section for today, and just double check that you're in the proper mode. We want to be in radian mode, not degree mode. Okay, so that's our decision-making process. We also have to make sure that we use the cast rule in decisions 2 and 3. So if I'm using a special triangle, or if I'm using my calculator, I have to be aware that my answer could actually fall into multiple quadrants depending on what the question tells me as far as like the quadrants and whether my answer is positive or negative. So we'll always make sure that we're aware that answers could fall in multiple quadrants. So I might have multiple answers to these questions is what I'm saying. Okay, this is helpful when I'm trying to find answers when I have a reference angle and I'm trying to find answers in other quadrants. And I'll show you how we use this one in our first example here. Okay, so find all solutions for cosine is equal to -√3/2. In the first rotation, so this is between 0 and 2 pi, that's a rotation all the way around here. So I actually have 2 answers where cosine could be negative in those 4 quadrants. So I usually just start by making a mental note. I might have 2 possible answers to this, but we're going to go through our decision process here. So decision process is, can I use a graph to solve this? The only time I can use a graph is if I have sine or cosine, which this one I have cosine. So I could potentially use cosine, but it must be equal to 0, 1, or -1. This one is not equal to 0, 1, or -1. So I will say no for graph, and I'll move on to the second process, the second decision process, which is, can I get this ratio from a special triangle? So what do you guys think? Can I get something like √3/2 from a special triangle?
Yes.
Yes, we can. Thank you, Keaton. That comes from a special triangle, so that would be a yes. And that will come from the pi/6, pi/3 triangle. So I'm just gonna draw that triangle here. Okay, and we'll use that in a moment. So because I'm using a special triangle, I'm gonna also use the cast rule here, and I'm gonna decide with a little picture here, which quadrants my possible answer could be in if cosine is equal to a negative. So can somebody tell me where we would expect our possible answers to fall when cos is negative? Keaton?
The sine and tan quadrant.
Perfect. So cosine is negative in the opposite quadrants where it's positive. Cosine's positive in all and cosine, a negative in sine and tan. So I'm going to just draw kind of like two arms coming out here so that I can visualize where my angles will be. We'll call this θ1 and θ2. You guys might remember this process a little bit from grade 11, slightly different in grade 12 because we're dealing with radians, but similar to what we did in grade 11. Okay, so here's my question. If I'm using this special triangle here and I have cosine, cosine is adjacent over hypotenuse. So I want this to be adjacent and I want this to be hypotenuse. What would be the reference angle that makes √3 the adjacent side? Would it be pi/3 or pi/6? Sarwa?
It would be pi/6.
It will be pi/6. So pi/6 is the reference angle that makes this adjacent. And of course, hypotenuse just stays the same no matter what our reference angle is. So our reference angle is pi/6. And the reference angle is always the angle that falls between the horizontal and each of my arms. So this angle inside here is pi/6. And this angle between the horizontal and my other arm will be pi/6 as well. So back in grade 11, the way that we calculated this was we found a reference angle and we did like, whenever this was like 180, we did 180 minus the angle or 180 plus the angle or 360 minus the angle. Now it's going to be pi or 2 pi, and we'll use whichever one is closer. And this is actually where these come in. So this is a nice little thing that will help you remember whether to do pi minus, pi plus, or 2 pi minus. But it should make sense as well. So I'll explain to you why we do that. This rotation is pi. This goes from 0 all the way to pi. And I want less pi/6 than that. So I want to get this part of the rotation right here. So I'm going to take the full rotation of pi, and then I will subtract pi/6 from it so that I can get the red rotation that I have labeled here. So that's the idea. So in order to find θ1, we're going to do pi minus the reference angle, which we can actually see in that quadrant. That's always the calculation that we use for that quadrant. So we're going to do pi minus our reference angle, which is pi/6. Okay, so create a common denominator here. This is going to be, I'll multiply the top and bottom by 6. This will be 6 pi/6 minus pi/6, which is 5 pi radians. or 5 pi over 6 radians, sorry, I should say. Okay, and then for theta 2, I want a full rotation of pi, and then I go past it by pi over 6. So I want to do pi plus an extra pi over 6 to get this full rotation around, like so. Okay, and we can actually see in this quadrant, we do the rotation of pi plus whatever the extra reference angle is there. So for theta 2, because it's in quadrant 3, we're going to do pi plus the reference angle, which will be pi plus pi over 6. So again, create that common denominator, multiply top and bottom by 6. 6 pi over 6 plus pi over 6 is 7 pi over 6 radians. Okay, you can perform a check. How can I check my answers here? What would I do? Bella?
Can't you just plug that into your calculator so that you would have like cos 5 pi over 6 and that should equal negative root 3 over 2?
Yes. So we will check in our calculator. Check cos of 5 pi over 6. So we're plugging each of these right back in to theta here. And you can also check cos of 7 pi over 6. You might not get negative root 3 over 2 out in your calculator. Like for instance, when I do this in my calculator, I get negative 0.866. And if I do negative root 3 over 2 in my calculator, I get the same thing. I get negative 0.866. So you might have to check the decimal values of those, but you should still get out. First, it should be negative, and second, it should give you the value of root 3 over 2. Okay. If I accidentally chose the wrong quadrant, the decimal answer will still be the same, but it might give me positive instead of negative. So you want to really make sure that you get out negative 0.866. Some of your calculators will give you out negative root 3 over 2. So, or check that it's giving you out negative root 3 over 2. Okay, so I should always know whether my answers are correct or incorrect for these questions. And always, wherever possible, we want to express in exact radian measure. And the way that we do that is by going through this decision process here. Okay, sometimes I may need to express this as an approximate radian value, which would be like a decimal answer. But wherever possible, exact values. Okay, that's a big difference between what we did in grade 11 for these questions and what we're going to do in this course. Okay, can I clarify any questions before we move on to another one? Okay, let's try another one. Find all solutions for tan is equal to positive 5 in the interval of the first rotation on the circle, so 0 to 2 pi. Okay, so we're going to go through our decision process again. And the first decision that we have to make is, can I get the answer for this from a graph? And the only time that I can get an answer from a graph typically is if I'm dealing with sine or cosine. And in this one, I'm dealing with tan. So I'm going to go with no on a graph for that one. Second is, can I get the ratio of 5 over 1 from a special triangle? I don't think we have any 5s in our special triangle, so that would be also a no. Final thing then, if I can't do any of those, is I will use my calculator. Okay. So I still draw a picture for this one. And I'm still going to use the cast rule because my calculator doesn't know that we have extra answers here between 0 and 2 pi. So where could my possible answers be if my answer is tan of theta is equal to +5, where would I expect my angles to fall? Clayton? I don't know if your mic's working there, Clayton. I don't think it is. There you go. He put it in the chat. Quadrants 1 and 3. Perfect. Thank you. Okay, so that would be the all quadrant and the tan quadrant. Okay, tan is equal to a positive. So this is going to happen where all trig ratios are positive and where tan is positive. Okay, just as a reminder, the reference angle always falls between the horizontal and the angle. So my reference angle will be here, and my reference angle will be between this horizontal and the angle. So it will be here as well. Okay, so on our calculators, if I have something like tan of theta equals 5, I can solve for theta by doing tan inverse. So we're going to make sure we're in radian mode, and I want to know what is the tan inverse of 5. And let's leave like maybe 3 decimal places here, nearest thousandth. Keaton?
Uh, 1.373.
Great. And this is a radian value, so we're going to put radians here. Whenever I do tan inverse of like a positive, I'm always going to get the answer in the all quadrant. And I know this is in the all quadrant. We'll call this theta 1. This is 1.373. I know this is in the all quadrant. Oh, sorry, extra decimal there. Because it falls between 0 and pi over 2. So if I actually calculate what is pi over 2 on my calculator, so we're going to type into our calculators pi divided by 2. That is approximately 1.57 radians. And I know 1.373 falls in between 0 and 1.57. So that's how I know that that's in the all quadrant. Okay. It's not going to give me the one in the next quadrant over. We have to find that. So we now need to find, so that will be our theta number 1. It's also going to be our reference angle. Okay, but it's also a solution. And that means that this reference over here will also be 1.373. But I want this full rotation. I want from 0 to pi plus that reference angle. I'm in quadrant 3. So in order to find, we'll call this theta 2. I'm going to do pi plus the reference angle. Okay, you can also look up here at this little kind of cheat sheet. So always pi plus the reference angle in quadrant 3. So we'll do pi plus 1.373. So right into your calculator, you're going to just press the pi button and do pi plus 1.373. And again, we'll leave 3 decimal places here. So nearest thousandth. Let me know what you guys get.
I got 4.515.
Perfect. And good rounding there too. So it's 5.4, sorry, 4.5145. So the 5 rounds the 4 up to 5. Okay, so that will be our answer for theta 2. Okay, I will check when I plug these back into tan in my calculator. So try tan of 1.373. It will be slightly off because we rounded, but it should be very, very, very close to 5. So I got 4.9896. So that looks good. And then you want to check tan of 4.515. And I'm getting like basically the same thing that I got for the other one. Well, actually, it's even closer. It's like 5.00017. So those are both good. We checked them both. Again, make sure that you get a positive value out of this because this is what we want. If you get a negative value, you probably found the wrong answer in the wrong quadrant. Okay. I'm going to change this one ever so slightly. I'm going to make this one a 2. Just so that I can show you a slightly different type of question. So 2 sine theta plus 2 equals 0. So when you're approached with questions like this, you need to first isolate for your sine x or whatever your ratio is that you're trying to solve for. So I'm just going to do reverse bedmass here. We'll move this over. Gives us -2. And then we'll divide out the 2 in front. And we have sine x equals -1. This is what we're solving for between 0 and 2 pi. So in the first rotation, we're going to go through our decision process for this. So decision process first starts with, can I use a graph for this? And what we want to ask ourselves is, am I dealing with sine or cos? Because those are the graphs that we're most familiar with, which I am. I'm dealing with sine. And is it equal to 0, 1, or -1? And that would be a yes for this one. This one's actually equal to -1. So I can actually use a graph to solve this one. And here's how I'm going to do it. I'm just going to sketch the graph of sine quickly here. Just the key points. So back from when we did transformations of our last unit, we know we have 5 key points here. This is what the graph of sine looks like. It always starts at a rising midline, rises up into a mountain. And my question is, so this goes from 0 to 2 pi, which is what we wanted. It's one cycle of sine. And I want to know, where is this equal to -1? Where would this happen? So this is pi over 2, pi, and 3 pi over 2. So where does this have a y value of -1? Okay, remember these are 1 and -1. Keaton?
3 pi over 2.
3 pi over 2. So that's happening right here. When sine is 3 pi over 2, y is -1. So our x from the graph must be 3 pi over 2. I could also potentially use like the unit circle for this, if you remember your unit circle back from unit 4. So I could look around and see where the y coordinate is -1 around the unit circle. But I think the graph is pretty easy because we already know the key points of sine. Sine is only actually equal to -1 at one location between 0 and 2 pi. So this one's actually only going to have one answer. Okay, any questions on this one? Okay, last one. And I think I might actually, let me just think for 1 second if I want to switch this. Let's switch this to cotangent, just so that we do one with a reciprocal ratio. Okay, so first things first, when we have questions that are in this format, we need to solve, not really solve, but we need to isolate for cotangent x. So because this is in brackets, when I do reverse bedmass, I'm going to first divide out that 3. I'll have cotangent x plus 1 equals 2 over 3. And then I'm just going to subtract 1 as I move it to the other side here. So I'll have 2 over 3 minus 1. Think of this as 1 over 1. Okay, I'm going to leave this in fraction form. We'll just do common denominator. And 2 over 3 minus 3 over 3 gives us negative 1 over 3. Okay. So now that we have this isolated, we're going to go through the decision process. So first decision we have to make is, can I solve this using a graph of sine or cos? And because this is cotangent, that would be a no. Can't use the graph of sine or cos to solve a cotangent one. Second one is, can I get a ratio of 1 over 3 from a special triangle? I can get a 1 over root 3 from a special triangle, but I can't get a 1 over 3. So that would also be a no. So then we're going to go calculator. Okay, so you're going to draw your picture. Write out your cast rule. And when I deal with questions that have reciprocal ratios, I actually like to prove the opposite. I like to prove the other primary trig ratio. And it makes it a lot easier because my calculator doesn't have the reciprocal ratios, cotangent, cosecant, and secant stored inside of it. So I'm going to switch this guy to its reciprocal ratio, which is tan x. And when I do that, I must reciprocal this ratio here. So if cotangent is equal to adjacent over opposite, tan must be equal to opposite over adjacent, right? I switch those. And so I'm proving, or I'm solving for where tan is equal to -3. And in doing that, I will prove, or I will, sorry, I keep saying prove, but I will solve the equation for where cotangent equals -1 over 3. Those happen at the same locations. Okay, so whenever you're dealing with a reciprocal ratio, you're always going to switch it to its primary, but make sure you reciprocal the ratio. And note that I left the negative here because we're not doing negative reciprocal, we're just doing reciprocal. So I want to solve for where tan x equals -3. Somebody tell me what quadrants my possible answer could be in here. Sam?
Cosine and sine.
Okay, quadrants 2 and 4. You're just going to draw an arm in there. I don't know where it goes. I just put it in there as a visual. And the reference angle that we need to find is going to be in between the horizontal and the angle. So this will be my reference angle. And between the horizontal and the other angle, this will be my other reference angle. Let's call this theta 1 and theta 2. Okay, so when we did this in degrees, this was a little bit easier to understand. When I did tan inverse of -3 in degrees, I would get something like, I don't know, 142. I'm just making that up, but 142 degrees. That's not the reference angle though. That's the angle for this first rotation here. And then we would need to find the reference angle. So the easy way to find the reference angle, instead of going through that whole process, is instead of taking tan inverse of -3, I take the tan inverse of the positive of that answer, and that will actually give me the acute angle that would normally fall in the all quadrant. That would be my reference angle. This makes a lot more sense than doing this in radians and trying to figure out like your reference angle after you get this first rotation. So in general, whenever I'm using my calculator from the decision-making process, I will actually first find the reference angle for these types of questions by doing the inverse of the positive ratio here. So I'm going to do tan inverse maybe we'll call, oh, sorry. I labeled these theta 1 and theta 2, but they're x1 and x2. Let's call that x1, x2. So maybe we'll call the reference angle just like theta. So theta will be equal to tan inverse of 3, not negative 3. So try the inverse of the positive of this. And the reason I'm doing this is because I want this acute angle that's inside here. I don't want this obtuse angle right here until after. So can you guys tell me what you got for the reference angle here? Tan inverse of 3.
I got 1.249.
Great. So this is going to be the angle that I would normally get from quadrant 1. That's an acute angle. That's what's going to be inside here. So we can actually even just put that in for our picture. So this angle right here is 1.249 radians. Same with this one. Then I want this rotation. So x1 will be equal to pi, because this is pi, minus the reference angle. So you can use that little kind of cheat thing that I gave you in the beginning of the lesson, pi minus the reference angle. So that will be pi minus 1.249. So let me know what you guys get. We'll leave 3 decimals again.
I got 1.893.
Great, thank you. Radians. So that's our first possible answer. X number 2. This is in our quadrant number 4. When we calculate in quadrant 4, we want a full rotation of 2 pi minus this extra little slice. Okay, so in this quadrant, we do 2 pi minus the reference angle. And you can see that at the beginning of your lesson as well on that little quadrant graph that we were using. So 2 pi minus 1.249. Let me know what you guys get to 3 decimal places.
5.034.
Thank you, Pero. And that's also radians. Okay. I like to just find the reference angle first, because if we find the reference angle, we can use that for both calculations. If I did tan inverse of -3, you guys can try that on your calculator. If we do tan inverse of -3, we actually get a negative, and that gives us this negative rotation here. So it just kind of makes things a little bit more confusing when we do tan inverse or the inverses of negatives. We want to just find the reference angle by doing the inverse of the positive and use the little short forms that we have up above, pi minus, pi plus, 2 pi minus. Okay. Maybe we'll make ourselves a note here just to find the reference angle. Take the inverse of the positive value. Okay, but just be aware this isn't an answer. This is just the reference angle that we'll use to find our answers. And we're still solving for this, right? We're still solving for where tan x equals -3. So when I check, when I plug in tan of 1.893, I should expect to get out something very, very close to -3. Okay, so just make sure you can do your check on your calculator. I'm getting out -2.995, which is good. So that one's good. And then we'll check in our calculator tan of 5.034. And I got -3.001. So that one is good as well when we check. Okay, so just make sure you sub back in to check. Okay, sub into tan x equals 3 to check. Can I answer any questions before I send you guys off to do some more work here? Okay,